Okay, so we got the video we watched yesterday of the big rolling rock coming down and trying to squish Indiana Jones. Okay, and so we were looking at this as a work energy theorem problem. Okay, the big rock was going to roll from here, where it had an initial speed of 0 meters per second, and was falling or rolling from an unknown height. Okay. We know that when it reaches the bottom of the tunnel, or the end of the tunnel where it seals it shut, okay, that it was moving at 4.5 meters per second and was as low as it could go, okay, essentially bottom of the ramp. So it would have a final height of 0 meters. Okay, so that's kind of what we started with. Now, the other thing we were told was that there was a force of friction of 800 newtons acting along the 30-meter length of the tunnel. Okay, when the rock gets to the opening, does it have more mechanical energy or less mechanical energy than when Indiana Jones triggers the trap? Is friction working for us or against us? Against us. That means it's converting some of the mechanical energy into sound and heat and other forms. So the rock will have less mechanical energy at the bottom, okay, than it had at the top. So we're going to set this up then. We're going to say that, yes, the mechanical energy of the rock is changing. Okay? It is changing because the force of friction is acting along the length of the tunnel, the distance, on the rock. Okay? That is going to cause the mechanical energy to change. Okay? And this is how all work energy theorem problems set up, but we're just kind of talking it through right now. All right? I need to expand these out. Okay? What I'm looking for is actually part of this. It's part of the initial mechanical energy. In fact, it is the initial mechanical energy. How do I know that? What I'm looking for is the height, which is part of the initial potential energy. Why am I saying the initial potential energy is the initial mechanical energy? Because the initial kinetic energy was 0. The rock wasn't moving at the beginning of this. And when we're at the end, all of the energy is kinetic. There's no potential. Okay? So what I'm going to do here is I'm actually going to move the initial mechanical over to this side by adding it. And then I'm going to subtract the work. Okay? Now, why did I do that instead of just moving the initial kinetic, or the final kinetic, sorry? I did that because I didn't want my answer to come out to be negative. Okay? Because that would have been confusing. Right? If I'd have got an initial potential energy that was negative, I might have got a negative height, and that would make no sense. That means the ball rolled out of a hole against friction, which doesn't seem plausible. Okay? All right, so now what I've got here is this. My initial mechanical energy equals my final mechanical energy minus the work. Okay, well that makes sense. Okay, work's the change in energy, the difference between the two. Yeah, that should work out. Okay, so we've already established that my initial mechanical energy is all potential. We've established that our final mechanical energy is all kinetic. And we've got force of friction, not equals. Times distance is the work. Okay? Now, what do I need to remember about this force of friction when I start plugging in my numbers? That it's negative. Now I'll be subtracting a negative, which will make my initial potential energy bigger than my final, which is what it's supposed to be. Okay? All right, so I want to solve for HI. What do I have to do with mg? Divide it over the other side. All right, now I can plug in my numbers. 1/2 times 400 kilograms times 4.5 squared. That was my final speed. Okay, minus 800 newtons. Times the 30-meter length of the tunnel. Okay, divided by 400 times 9.81. Okay, so I'm putting in that negative there. I forgot to write it here, but I'm putting it in the calculator. Okay, so the rock fell or was triggered from a height of 7.1 meters. Okay, and that should be fairly accurate. Okay, Harrison Ford, when he triggered the trap, went like this because he heard the sound of the rock and he looked almost straight up. He's almost 2 meters tall. Okay, and what he was looking at was way above it. Okay, so it would fit that this was at about 7 meters high. All right. Those are about as tricky as they get, okay, in terms of work energy theorem questions. We'll work on some that are easier than that, okay, but those are about as tricky as they get. All right. So what I would like you guys to do is get the digital workbook open here. I'm going to pick a few questions out of there that I'd like you to do. Okay, I would like you guys to work on, let's say, number 3, number 4, and number 8. 3, 4, and 8. Okay. And that'll take us for sure to the end of class today. So 3, 4, and 8. Looking at question number 3, why is the answer 0? Yeah, you're holding it perfectly still. You're not changing anything about it. It's potential energy. It has some, but it doesn't change. You're not lifting it or lowering it, and you're not making it go faster or slower. So basically, that's a question that asks, do you remember the definition of work? Okay, and that it's a change in mechanical energy and that that's not happening here. Okay, that's really all that question is asking.